Alright, let's talk about SHAP, which stands for Shapley Additive Explanations. This is another powerful tool for explaining machine learning predictions. SHAP brings together several interpretation methods under a single framework based on game theory. And the goal is to assign each feature an importance value for a specific prediction by using something called Shapley values. And these come from cooperative game theory, and they are a way to fairly distribute contributions among a group of players, in this case the features of your model. And here four concepts and some ideas. The core idea behind SHAP is that it assigns each feature a contribution value for a particular prediction. These contributions show how much each feature has impacted the prediction compared to a baseline value. So, if you are wondering why your model predicted a certain outcome, SHAP has break that down by attributing the prediction to individual features. And what are some key properties? Here you can see locally accurate, missingness, consistency, and additivity. But let's look at locally accurate. This means that the sum of all the feature contributions will exactly match the model's original prediction. It ensures that nothing is left unexplained, which is important for transparency. And here, missingness. Here, if a feature has no impact on the model's prediction, SHAP assigns it a contribution value of 0. And this is useful because it helps eliminate noise and focus only on the features that actually matter. And here, consistency. This property ensures that if features contribution increases in a model, SHAP will reflect that change predictably. It's a guarantee of fairness. More impact should mean more attribution. And finally, here, additivity. What's that? Here, SHAP ensures that the contributions from all features add up to the difference between predicted value and the base value. And the base value is typically the average prediction across the dataset. So this property ties everything back to a meaningful reference point. In summary, SHAP is grounded in strong theoretical principles and ensures that feature attributions are accurate, fair, and interpretable. And your game theory foundation. Sorry. This is where the mathematical elegance of SHAP comes from, particularly its use of Shapley values. And let's break this into two parts. What Shapley values are and how game theory concepts apply to SHAP. And here, the concept of Shapley values comes from the game theory and was introduced by Lloyd Shapley in 1953. And the main purpose of Shapley values is to provide fair allocation of payout among the players in a cooperative game. And you can think of it like this. If a group of players work together to achieving something, how do we fairly divide the rewards of or benefits among them based on their contributions? Shapley values answer that question mathematically. In the context of SHAP, the players in this game are the features of your dataset, and the payout is a modest prediction. And the idea is to distribute the prediction, or the difference between the prediction and the baseline, fairly among the features based on their individual and combined contributions. And here's some analogy, and let's get this. To better understand how this works, we will break it down into game theory terms and relate them to SHAP. Here you can see players equal features. In this analogy, the players are the individual features of the dataset. Each feature contributes to the final prediction, just like players contribute to the outcome of a game. And here coalition, I mean a subset of features. Here a coalition uh, represents a subset of features working together. In SHAP, we consider all possible subsets of features to understand how each feature contributes in different contexts. For example, what happens to the prediction if a certain a certain feature is included versus excluded from the coalition. So, what's game? It is prediction task. The game here is the task of making a prediction using machine learning model. The goal is to determine how much each feature contributes to the success of this game, in other words, the prediction. And here's payout, and it is difference from the average prediction. The payout represents the contribution of the features to the prediction. Specifically, it is the difference between the predicted value for a specific instance and average prediction. The Shapley value allocates this difference to each feature in a fair and consistent way. So, how it all comes together, SHAP uses these Shapley values to ensure that every feature gets its fair share of the prediction. And this fairness is based on the idea that each feature's contribution should reflect its marginal impact when added to the different subsets of features. And by considering all possible coalitions, SHAP ensures that the contributions are calculated in a way that's mathematically rigorous and interpretable. For this slide, the foundation of SHAP lies in game theory, and its use of Shapley values ensures fairness in attributing predictions to features. And what's next? Alright, here's math. So, let's start with the formula for calculating the Shapley value of a specific feature, and it's denoted as pi sub I here, or p sub I. This this value quantifies how much a particular feature I contributes to model's prediction. And here the formula, and let's break this down step by step. Here, this. What's that? Summation overall subset S of n excluding I. What's that? This symbol tells us to sum overall possible subset S of the feature set n excluding the specific feature I we are evaluating. And this ensures we consider every possible coalition of features. And here, S factorial, you can see this is the factorial of the size of the subset S, and it represents the number of ways to arrange the features in subset S. And what is that? Here, this 3 factorial of the size of n minus s minus 1. These 3. This term accounts for the arrangements of features not in S but excluding I. And here n factorial, this is the total number of arrangements of all features in the full feature set n. And what happens here? Value of S union I minus value of S. What's that? This represents the marginal contribution of feature I when it's added to the subset S. Essentially, it's the difference in the model's prediction when feature I is included versus excluded. So, the formula calculates the weighted average of I's contribution across all possible subsets. And I'm looking here, the value function denoted as well here maps subsets of features to predictions. For instance, it evaluates the model's prediction when only the features in S are considered. And it handles missing features through marginalization. Essentially, it calculates predictions by considering the potential values of missing features. And The value function also considers all possible feature combinations to ensure that every scenario is accounted for when calculating the contribution of a feature. And sorry, here again what we can say. The weights in the formula are based on the size of the coalitions, I mean S. And this ensures that each subset is weighted appropriately. And I'm looking here, I mean the weights are expressed as like that, and this term ensures fair attribution by considering all possible orderings of features. And the factorials that ensures that each feature contribution is weighted consistently across all subsets. So how it all fits together here, the SHAP value formula is designed to ensure fairness and completeness. Each feature's contribution is proportional to its marginal impact average across all possible subsets, and the sum of all Shapley values for a prediction equals the total difference between the prediction and the baseline value. So, this framework guarantees that the attribution of feature importance is consistent, rigorous, and interpretable. And I hope that page is okay. So here, extensions. You can see these extensions are designed to handle specific types of models and scenarios, and here we will cover three key extensions: kernel SHAP, tree SHAP, and tip SHAP. First, we have kernel SHAP. This extension is a model agnostic approach, meaning it works with any type of model regardless. Sorry. Okay. What I say, regardless of how it's built or what algorithm it uses. And kernel SHAP uses weighted linear regression to compute Shapley values, which allows it to approximate the contribution of each feature to the prediction. And it's conceptually similar to the line, but instead of local explanations, it calculates exact Shapley values, making it more theoretically robust. And kernel SHAP is versatile because it can handle any type of model, from neural networks to ensemble methods. And in 3D SHAP, next we have this. It's typically designed for tree-based models like decision trees, random forests, and gradient boosted trees. And tree SHAP is highly efficient because it reduces the computational complexity from exponential to polynomial complexity. And this extension guarantees consistent feature attribution, meaning that if a feature has a larger impact on a prediction in a tree, it will be reflected in the overall explanation. And additionally, tree SHAP is very good at handling interaction effects between features, making it well suited for scenarios where feature influence predictions in combination. And here deep SHAP. It is tailored for deep learning models, and I think you predicted. And here it combines two powerful methods: deep lift and Shapley values. This combination allows deep SHAP to efficiently compute feature contributions even for complex neural network architectures. And one of the advantages of deep SHAP is its ability to handle the unique characteristics of neural networks, such as the relationships between hidden layers and input features. It's optimized to ensure computational efficiency, which is important when working with large and complex deep learning models. And let's move on to here local accuracy. So it is one of the key theoretical properties of SHAP. This property ensures that SHAP values provide an additive explanation of the model's prediction for a specific instance. And here you can see the formula, and let's break this down step by step. Here f of f of x. This represents the model's prediction for a specific instance x, and it is the output of the machine learning model when given the input x, and this p sub 0 or pi sub 0. This is the base value, which is essentially the average prediction of the model across the entire dataset. And you can think of it as the baseline or starting point for an explanation. Every prediction begins at this base value, and the SHAP values then adjusted. And what is that? The summation of pi sub I of x overall I. This is the sum of the SHAP values, where pi sub I of x represents the contribution of feature I to the prediction for instance x. And each feature's SHAP value quantifies how much that feature pushes the prediction away from the base value. And how it all comes together, the formula ensures that the prediction, I mean fx, is fully explained by the sum of the base value, which captures the global average behavior of the model and individual contributions from each feature. And this property is important because it guarantees that the SHAP explanation is both complete and accurate. The contributions of all the features together plus the base value exactly reconstruct the model's prediction for the given instance. Nothing is left unexplained. And local accuracy is what makes SHAP trustworthy as an interpretability tool. It ensures that explanations are consistent with the model's predictions, and you can clearly see how each feature contributes to the final outcome. This is particularly important when you need to justify predictions in high-stakes scenarios such as healthcare or finance. And here efficiency. What is that? It states that the sum of all SHAP values equals the difference between a model's prediction for an instance and the base value. And you can see the formula. And let's break this down here. Summation of pi sub I overall I here. This represents the total contribution of all features, where each pi sub I is the SHAP value for a specific feature I. And this f of x, this is the model's prediction for the specific instance x, and it is pi sub 0. This is the base value, which represents the average prediction across the dataset. And in simple terms, the efficiency property ensures that the SHAP values fully account for the difference between the model's prediction and the base value. There is no extra or missing contribution. Everything is accounted for in the SHAP explanation. And additionally, you can say there is a symmetry. Symmetry ensures that if two features contribute equally to a model's prediction, they will receive the same SHAP value. It doesn't matter what order features appear in or how they are combined. If their contributions are identical, SHAP will treat them fairly. And for example, if two features both have the exact same impact on the model's prediction, the symmetry property guarantees that they will be assigned equal SHAP values. This is important for maintaining consistency and fairness, especially in datasets where certain features might be interchangeable or equally important. And it is nothing in the slide, but I want to talk about some computational considerations. This is an important topic because while SHAP provides powerful and accurate explanations, the computation required can sometimes be a challenge. And I will break this into two sections now. exact computation and approximation methods. And first, exact computation. What's that? Here's the issue. Theoretically, SHAP values are computed by evaluating all possible subset of features. And for a data set with features, this requires to the power of the size of the features evaluations. And here's exponential growth, and that means the computation becomes infeasible as the number of features increases, especially for large datasets or complex models. And however, this approach guarantees theoretical correctness, making it the most precise method for calculating SHAP values. And secondly, there are approximation methods. To address the computational challenges of exact computation, SHAP also provides approximation methods, and these methods are designed to balance the trade-off between accuracy and runtime. And here, the two main categories, and here sampling-based approaches and model-specific optimizations. And what are they? To talk about the sampling-based approaches, these methods approximate SHAP-play values by sampling coalitions instead of evaluating all possible subsets. And by strategically sampling, we can get reasonably accurate results without needing to compute every single subset. And this approach is particularly useful for models with a large number of features. And for model-specific optimizations, we can say SHAP offers specialized methods tailored to specific types of models. And these methods leverage the structure of the model to speed up the computation. And here we have a trade-off between accuracy and runtime. The choice between exact computation and the approximation methods often depends on the specific use case. If you need precise, theoretically guaranteed SHAP values and the dataset is small, exact computation is ideal. And for larger datasets or more complex models, approximation models like sampling or model-specific optimizations are a better choice. They reduce computation time while still providing interpretable and reliable results. And that's all, everybody, for introduction to SHAP, and thank you for listening. See you in the next topic.